So question 2 starts out with acids and bases, and it's a little bit different from normal, so it's important that you don't get scared off by this slightly weird thing, HXA. What that means is that it's an acid, and we're not going to worry about what the A bit is. You know, when they use a shorthand like that, it means it doesn't matter what it is, so it's tartrate, but we're not going to worry about what the formula of that is. The important part is this X, which is a particular number of protons that acid provides. In other words, it's saying that each mole of H3A can provide X number of moles of H plus ions. And the way we're going to find out what X is equal to is by looking at the reaction with sodium hydroxide. So I think it would help, if you're worried by that, to just think about more familiar acids and the equations for their reaction with sodium hydroxide. So if we take HCl, where X is 1, okay, there's just one proton provided by each HCl. The equation for reaction with sodium hydroxide is very simple. Remember, acid plus alkali goes to salt plus water. You must be very sure that you remember those essential acid reactions. So it's a one-to-one reaction, reflecting the fact that each H plus ion from the acid needs an OH minus ion from the alkali to react with. If we switch to sulfuric acid, which is H2SO4, okay, so now X would be 2 if we represented it with that shorthand, then the equation now requires 2 moles of NaOH to balance it up, because we get Na2SO4 and 2 moles of water. So the important thing that you can now hopefully begin to see is that the relative number of moles of alkali to acid tells you how many H plus ions are made available by each molecule of the acid. So here twice as many moles of NaOH as H2SO4 are required, and that tells you that X is 2, that there are 2 H plus ions made available by the acid. So let's see how that pans out with tartaric acid, which is what they're asking about here. And the first thing it asks you to get is the moles of HXA, the tartaric acid. When you're working in solution, as we are here, what you should expect to use is moles is equal to concentration times volume in dm cubed. So it's absolutely essential, first of all, that you remember that relationship, get it the right way round, and that you think of using it when there's solution chemistry. And there's always going to be clues in the information. You know, if it's talking about concentrations and volumes, if you recognise the units, moles per dm cubed for concentration, dm cubed for volume, they should prompt you to use that relationship. Okay, so what are the numbers we need? Just be careful to get it the right way around. There's obviously a lot of numbers there, make sure you get the right ones. So for the tartaric acid, concentration is 0.0500 moles per dm cubed, and the volume is 25.0 cm cubed, but you must remember that has to be divided by 1,000 because it's got to be in dm cubed. Okay, so cm cubed you divide by 1,000, so times 25.00 over 1,000 equals what does that come to? 0.00125 moles of HXA. Okay, so that's the answer to part A. Part B is exactly the same kind of calculation, but now applied to the sodium hydroxide, because remember, we're just going to compare the relative number of moles. So we get moles of NaOH, again is concentration times volume in dm cubed, but this time, for the sodium hydroxide, the concentration is 0.200, and the volume, it tells us, is 12.5 cm cubed, which is 0.0125 dm cubed once you've divided it by 1,000. And that comes to 0.00250 moles of NaOH. Okay, so we've got these two numbers of moles, and to get the ratio, of moles of sodium hydroxide to moles of H3A, you just divide that number by that number, and you can probably do that in your head without needing your calculator. You can see you need twice as many moles of NaOH, and that gives you the answer to part C, to part 3. So the answer is that because you need twice as many moles of NaOH as you do of HXA, that means that X is equal to 2. You could write that as an equation if you wanted to, although you don't need to. If you say X is equal to 2, the formula is H2A, and that reacts with 2 moles of NaOH to give you Na2A plus 2 waters. Okay, but you don't need to write it in the form of an equation. You can simply say that because you need twice as many moles of NaOH as of HXA, then each mole of HXA must provide 2 moles of H plus ions, and therefore X is equal to 2. Right, the next bit then switches to copper nitrate, and it's telling us that we're going to prepare copper nitrate by dissolving copper oxide in nitric acid. So again, this is one of those reactions that you need to be very sure about. Acid plus oxide goes to salt plus water, and it asks us for the equation. Notice this time it doesn't say state symbols. You can put them in if you want to, provided you're sure that you know what they are. But if it doesn't ask for them and you're not sure what they are, then better not to put them in, because you don't want to put things in that are wrong. That's a really important general principle. Don't, in general, try and give them extra bits of information that they don't ask for, because there's always a risk, if they're wrong, that you'll end up losing marks that you needn't have done. Okay, so the equation is acid plus oxide goes to salt plus water. Copper 2 oxide is CuO. It's important you don't just guess that you stop and think about it. And where that comes from is the fact that copper is 2 plus, that's what the Latin number 2 tells you, and oxide is 2 minus, because oxygen's in group 6, so when it forms negative ions it will take 2 more electrons to reach 8 where it stops. So the charges balance and you just get CuO. Okay, so CuO reacts with nitric acid is HNO3, and notice that they didn't give you the formula of nitric acid, and that's a really important reminder that you need to know nitric acid, and you need to know sulfuric acid, H2SO4, and hydrochloric acid, HCl. They will assume that you're familiar with those chemicals and that you therefore know the formula. So that gives you copper nitrate, and they were kind enough to give you the formula of that. But you can see where that comes from. Copper is 2 plus, nitrate is 1 minus. So hence that formula. And the other product will be water. And you can see that it doesn't balance. We've got 2 nitrates there, so we're going to have 2 nitric acids. And once you've done that, that's fine, that does the job and it balances. Then it's asking you about the bonding in copper nitrate and simply says what's meant by ionic bonding. So again, it's in your definitions list. You've got to make sure you've learnt it, and the definition is that it's the electrostatic attraction between oppositely charged ions. The most important thing in that is that you've got to say oppositely charged ions, not just attraction between ions. Don't necessarily need the word electrostatic, but it's a good descriptor. Okay, now we've got to explain why a solution of copper 2 nitrate conducts electricity. It's only 1 mark, so it's a very simple idea, which is simply that the ions are mobile in the solution. So in conductivity questions in general, remember what you need are either mobile ions or mobile electrons. Either one of those will give you conductivity. But when it's an ionic compound that's doing the conduction, whether it's in the solution, as here, or in a molten state, it's the ions that are mobile. There are no mobile electrons. And if you suggest that there are, even if you say mobile ions as well, you won't get the mark. Mobile electrons is what you get in metals and in a few other materials like graphite. But here, it's the ions that are mobile. Right, oxidation number of the nitrogen. So we've got CuNO3 twice. So Copper, we've already decided, is copper 2 plus. The Roman 2 told us that. So the oxidation state of the copper is +2. Oxygen in compounds is always -2. Again, that comes in the rules that you need to have memorised. So you've got 6 oxygens, right? 2 lots of nitrate ions, which each have 3 oxygens, so 6 oxygens altogether. So that gives you 6 lots of -2. And you can figure out the nitrogen then by remembering that the sum of the oxidation states of each atom in the formula of a neutral compound like that has to be 0. So at the moment we've got +2 from the copper, -12 from the oxygens takes us to -10. And therefore these 2 nitrogens, again notice there's 2 nitrogens, those between them have to add up to +10. And so it's 2 lots of +5. Okay, so the answer is +5 is the oxidation state of the nitrogen. Now we've got to think about hydration of this ionic compound. So water crystallization is a popular topic in AS level exams. And again, this is a slightly different question than the ones you've done before, but it's important first of all that you remember what water crystallization is. That any ionic compound could, when it crystallizes out, potentially bring waters with it out of the solution. So the idea is that copper nitrate, when it crystallizes, actually brings waters out of the solution, and they form part of the crystal, and so it forms crystals which have that formula, copper nitrate dot X number of water molecules. And all it's asking us to do here is to figure out what X is, how many water molecules are there. So if you look at the empirical formula it gives us, you can see it's got 1 copper, which fits with that, it's got 2 nitrogens, which fits with that, and it's got 12 hydrogens. So there are no hydrogens here, all the hydrogens are in H2O. If there are 12 of them, that must mean 6 waters. And we can just double check, and we must double check that that fits with the oxygens as well. So the total is 6 oxygens there, plus another 6 makes 12 oxygens altogether, which is indeed what it gives in the empirical formula. So that's the answer to the question, and that's the end of question 2.